Professor Descotes-Genon is already here, and this is going to be the last lecture of this week of flavor. So I thank Sébastien for his interesting lecture, and I hope you enjoy this one as the other ones. Okay, so whenever you are ready, you can start.
Okay, thank you very much, Julia. Okay, so hello everybody. So indeed, that's the last lecture for this week. So I just remind you a bit. So we had a brief discussion of flavor physics, mostly in the standard model, how flavor arises. Then we looked at a few tools that we're using very well, most all the time when we're dealing with flavor problems because of the interplay between the various scales, electroic scales, the QCG, especially in the non-perturbative regime, so the low scales that are also involved, and how we can separate and treat them differently. And then we moved to the question of how we could use all this in order to determine the parameters of the standard model concerning flavor, especially the ones regarding CP violation. And I showed you elements of that, how you could use many different constraints in order to over-constrain the parameters describing the CK matrix, and how you could, in the end, obtain a very good agreement, at least concerning the processes that have been selected in order to determine the structure of the CK matrix. So that means that at least in some parts of the flavor processes, everything seems to be in a very good agreement with the standard model, and especially concerning the fact that CP violation is described by a single parameter, that is a phase that is present for the quarks in the CK matrix, and that rules everything concerning CP violation. Now, for the last lecture, I'm moving to different topics where things seems to go a bit awry and not being in very good agreement with the standard model. That's what has been called anomalies. And so at least B flavor or B quark anomalies. After a while, people have started using the term to denote anything that is deviation in the flavor sector. I will focus on two different subsets of anomalies that at least seem to be quite promising. And so those anomalies are actually, so this is something that has emerged over the last decade, I would say. And so potentially, so they are both for big quark decays. And so potentially related. And at least you don't have to make huge efforts concerning, you can even already not even have a general model for new physics, but already at the level of effective theories, you can try to relate those different subsets. And so those ones are concerning first B2CL new that we already discussed in the context of determination of VCB, sorry, not VUB. And then B2SLL that we also discussed a bit when we discussed VTS, because that was one way, well, B2S gamma, actually not B2SLL, but that belongs to the same category, that have been used in order to extract some information on VTS. And so in the standard model, one of those two processes, so B2CL new, as we know already, is something which is mediated by W directly. So it's a tree process, charged. Whereas when we're looking at B2SLL, then we're clearly flavor changing neutral current. So here it's a loop process, neutral. And so obviously already at the level of the standard model, so you have to take into account the CK matrix elements, obviously, but the fact is that you expect one of them to have a strong component from the standard model, whereas the other one is actually very much suppressed in the standard model. And so obviously you can think of looking at this in different settings, considering whether a spin 0 or a spin 1 final state, and that's true for both B2C and B2S. So you can also imagine to play with the fact that you've got possibility to have also a BS. Actually, well, yes, you could imagine doing things like BS to have 0 into a scalar. Same thing here, you could imagine to have S's here and there. But mainly what has been looked at is B2D, B2D star, B2K, B2K star, BS to phi. So this one I will not consider here. You get also the possibility to, and that was back to the question that was asked yesterday, to look at baryons. So lambda B baryons are the structure of a lambda B lambda, but by replacing the S by B. And so that tells you that you can have these kind of processes. And when I'm writing these processes, they have been actually been considered and measured. So different hadronic processes where they can be considered. And then you do have the fact that you see deviations. So several sigmas that can go up to 3 sigma for individual measurements. So for B to C, that's actually related to measurement when you're comparing the decay in the case where the lepton is a tau, and the situation where it's a light lepton, and I'll come back to that. And then you have, interestingly, also measurements, similar measurements, where so you're doing the same kind of comparison, comparing B to S transitions where you have muons versus electrons in the case of the flavor changing neutral currents. So the point is that actually you can ask why do we do that this way? Why don't we compare each individually? And also, why don't we have why do we say that we can take E or mu equivalently, and why don't we consider B to K star K tau tau? So the question is a bit different in both cases. In one case, for RD star, actually, for the moment, up to a small footnote I'll mention later, we don't see any differences between electrons and muons for those processes. So it's B here, not D, B to D star and mu. So we can consider both equivalently electrons and muons and compare to the tau where there is a difference. And the differences do not only come from kinematic differences, the fact that the masses are different. They actually, when you do the computation, and I come back to that, you do see a difference. So you see that there is something not talking to the tau in the same way as it's talking to the electron and the muon. For the K star, so here we're comparing electrons and muons. We don't have information for the taus. It's first of all because it's very challenging, and also because the rates are not at all the same. So that means that we're limited for the moment in probing the third family for the leptons for this. But so you do have deviations for these ratios that are actually, you could say, there are probes of lepton flavor universality, which is actually something important in the standard model. In the standard model that we described very quickly during the first lecture, you saw that there is nothing differentiating the interactions of the leptons. And so that means that in principle, this is a very strong element to probe the standard model if you see deviation from the flavor universality. Moreover, in the case where you're looking at B2SLN, so you have other observables that are indicating deviations from the standard model expectations, and that's both at the level of the branching ratio for B2S mu processes, and also for angular observables, also for B2S mu processes. Whereas for the B2SEE case, you don't see any deviation. Obviously, the statements are within the theoretical and experimental uncertainties currently available, but clearly there is something going on more for the B2S mu transitions than for the B2SEE transitions concerning deviations with respect to the standard model. And those deviations, they occur not only at the level of the decay rate, but also at the concerning the geometry of those processes, and more specifically, so for the branching ratio, it's not only it's B2K mu, B2K star mu, BS25 mu, but for the angular observables, you will see that it's actually more related to B2K star mu. And so just in order to make this a bit less sketchy, maybe I will just show you for 1 minute the situation that you have experimentally. So this is the first, for the first kind of processes, so B2C LNU. So you see that actually you have here the 2D plot where you've got RD on one side and RD star on the other side. You have measurements from various experiments. So some of them are actually quite old. I mean, Barbara has actually stopped working for already quite a while now, even though they're still reprocessing some of the data. And then you've got Bell and LHCb, which are two experiments of importance of flavor physics in the B sector. You have measurements in the 2D plot, meaning combined measurements of both. You have also, so that's mainly for B factories producing B meson through the decay of epsilon 4s. And then you've got LHCb working at the LHC, so through producing B through PP collisions. And actually, it's more difficult for them to work on RD than on RD stars, which explains why they give mainly bands constraining on the RD star. And you see that the average of all the various constraints give this constraints, so these values for RD and RD star, compared to what are the standard model value measurements, which are quite away. So in the end, it's combined. It's 3.4 sigma when you're taking in the 2D plot, that you're away from experiment, between experiment and theory. So probably I will just keep on with B2C, and so I come back to stop sharing here and come back to sharing here. And so, before, well, I will keep on with B2C. Sorry. So actually, just for completeness, I mentioned that you had these deviations in RD star. Actually, you do have other constraints for B2D star tau nu. Actually, from the angular analysis of this, you can actually have information on the longitudinal polarization. of the D star. In principle, you have 3 different polarizations available for D star, and then you can look at how they're easily you produce a longitudinally polarized D star compared to the other ones, the other polarizations, and you can also look at the polarization of the tau meson, tau lepton, sorry. So this one is actually by looking. So in both cases, what you do is you look at the further decay of either the G star or the tau into a rho or a pi, and actually both of the measurements, which are related to the geometry and not just the decay rate, RD star and RD are related to RD and RD star are related to the decay rate, whereas these ones are related to the geometry of the decay, angular observables, and actually they are both in good agreement. One other thing that I should mention that has been also studied is the situation where you're using a BC rather than a BD meson to start with. And so you got a charm spectator quark, and so but the decay at the quark level is still B2C and mu B. And so you can once again build the same kind of ratio comparing the tau, the branching ratio of the tau, and the branching ratio with others, lighter leptons. So the 2 things is that actually it's difficult because the form factors entering are not so well known. And so the uncertainty on the theoretical side is quite large. But the second point is that the central value is actually very low, so hard to accommodate with the current form factors. So I'm not going to spend too much time here. The only point, so the point is that it's so the central value is actually quite low, but it goes. The only thing, so even though the uncertainties are quite large, the interesting point is that you will find a similar trend in all the cases concerning the branching ratios. So the branching ratios measured are all larger than the standard model expectations. Remember that the cross concerning the standard model was low compared to the experimental measurement for RD star. And actually the situation for BC is also similar in the sense that you do seem to have the same kind of trend concerning all sort of general scaling of all RD and all lepton flavor universality violating probing ratios, whereas at least for B2D star tau nu, you don't seem to have any kind of deviations at the level, at the accuracy at which measurements are performed. Okay, so the question is obviously how to interpret these deviations. And the answer again will be the notion of effective Hamiltonian. Why this time is it a good tool? So I already used this idea that it's a good tool for standard model analysis, but actually what you can do is just, as I proposed, is that you just add new physics as additional operators to this effective Hamiltonian. And then actually you can just do the analysis in a model independent way. by considering all dimension 6 operators that you can build in your effective Hamiltonian, and then determining the values of the Wilson coefficients from data. Once you've done this, so this part is completely independent. You're considering all possible modifications at short distances allowed within your effective framework. So this is something completely general. And then once you have this, you can imagine so you got an idea of what are the Wilson coefficients affected by new physics. Then you can, from that, build models that will exhibit the required deviations from the standard model in the Wilson coefficients. And if you remember the discussion that I had at the beginning when I introduced the notion of effective Hamiltonian, I started with Fermi theory, saying, okay, you can integrate out the W and then you end up with the Fermi theory, but actually imagine that you live, as at some point in the past, we lived in a world where you don't know only the Fermi theory and nothing more, nothing about the general structure of the standard model, then the size of the Wilson coefficient gave you still, which was GF, the Fermi constant here, the size of this short distance Wilson coefficient is telling you something about the typical scale of the physics that you have integrated out. And then the structure of the operator that you had at the end told you something about what were the requirements of the underlying theory, because you had gamma mu matrices suggesting a spin-one exchange, and then you had the fact that you were only involving left-handed fields. So that gave you already quite significant constraints in the direction, concerning the direction in which to look for new field, well, for additional degrees of freedom, so the W in this particular case. And here we're playing a bit the same game. We see things that we try to interpret in a general model-independent approach to start from. And then once we know which are the Wilson coefficients which are affected by new physics, deviating and explaining the data, then we will be in a situation where we can start to imagine models that will be able to actually do these particular modifications without altering the rest of the picture, so that you keep the agreement with the standard model. So that's the general idea, and so that's the second way of using still the decoupling between short distances and long distances implemented in this effective approach. Okay, so if you do that, so you can think of what would be the effective Hamiltonian that you want to use in order to perform this program. Okay, so at the level of the standard model, that's an almost trivial thing, because you got only the this kind of diagram when we are looking at the standard model, and you're performing the integration that I just mentioned in order to have a four fermion operator in the standard model. And so actually in the end, you can do exactly the same. So your Hamiltonian will be something typically, you can take out some factors that, because you think that the standard model will be a good starting point. Obviously, you could also put these factors that have been factorized in front inside the Wilson coefficients. Here it's just because it's easier to deal with that, but in general, you could just put them back and do the analysis exactly the same way. And so in the standard model, you've got only one operator or odd friend. And the Wilson coefficient associated with this operator is 1 in the standard model, and same for all 3 leptons. If I wanted to be more specific, I would have just to say, to put some kind of index here reminding me of the fact that I got actually 3 different effective Hamiltonians, one for each of the 3 generation of leptons. In the presence of new physics, then I can have modifications of the short distance Wilson coefficient. The Wilson coefficient CLVL, and the modification does not have to be the same for all 3 leptons, potentially lepton flavor universality violating. So that would be an explanation for the fact that you do find different branching ratios for the tau and the electron and the muon. But then you can also think of additional operators, so it's just that you write down all the possible operators. It turns out that some of them do vanish in the standard model, but you can consider all of them. So you can just say I can have chirally flipped operators where I'm changing the chirality of the quark fields that are involved. I could imagine to have also scalar or pseudo-scalar operators. So one example of that would be this one. So that means that actually the couplings of the chiralities involved are going to be different because of that, because here that wouldn't be right, but right, left, for instance, not left, not right, but right, left. And then I can also imagine to have tensor operators. And then when I've done that, actually I've exhausted the possibilities that I can write at dimension 6. So it's at least it's a fairly tractable problem. You have to, I just put P left everywhere. So it's P left, not B left, P left here. I have I've put only P left for the lepton part, because I've assumed that you've got only left-handed light neutrinos that have to be considered. Obviously, you could do a similar thing if you started. You could add new operators if you believe that you had also light right-handed neutrinos. Okay, and so the idea is that you can compute all the observables as functions of decay amplitudes, which will be of the form of Wilson coefficients time form factors, and those form factors will be related to the various matrix elements on the hadronic part, and so that would be obtained from, for instance, if you're looking at a D star, C bar, and some kind of structure and gamma. Once again, as before, everything related to the leptons can be expressed very easily, so I'm not talking about this. And the idea is that once you've done that, you can see all your observables, measured observables, as sets of constraints on the value of the Wilson coefficients, as long as you do have good information concerning the form factors. So I discussed already quite extensively the issue of the form factors concerning B2C transitions. The only thing that I want to add is that, so concerning the form factors and the observables, so here you have more form factors than in the standard model, since you take into account all the operator structures. You see that you got something like a few of operators that can contribute with different structures, axial, vector, scalar, pseudoscalar, tensor, and various cases. So that means that when you're looking at the, for instance, a B2D and nu, you have our old friends F plus and F0 or F plus and F minus, but you do have also a third form factor related to the tensor matrix element. For B2D star and nu, same situation goes. You have the ones that we have introduced already, but you've got also three other form factors that are present for the tensor part. And so that means that you do have quite a few more form factors to compute from lattice QCD, for instance. Actually, it turns out that it's a bit complicated to have, for the moment, completely accurate information on this. So you have generally to combine that with information from HQET, and then to extrapolate, assuming in Q square from the data, assuming that new physics is, well, negligible in electrons and muons. So that's the situation is improving, as actually now there are more accurate determinations for these form factors. So it's getting better, and it's still compatible with the previous determinations. So it doesn't seem to be much of a problem for the moment. Okay, so now I said that I could compute, for instance, the branching ratios using these operators. So you see that I get Wilson coefficients times the various form factors here. Actually, I wanted to highlight also another aspect, because that might be still useful to have in mind, is I'm not going to do the full angular analysis of B2D or B2D star, but it's just to give you just a hint of how this kind of computation is carried out. So really going up to the determination of geometrical description of the full decay. So for instance, if I'm looking at B2D star and nu, and the D star is actually going to decay into a D pi through strong interaction. So typically what you have is, so you have two different planes to be considered. So you start with a B, and then on one side there is a D star flying, and at some point it will decay into a D and a pi. So here you will have a D star contribution here. And then on the other way, you've got your lepton pair. So obviously, I'm drawing this in a way which is clearly not completely correct, because you see that actually it's as if I drew, and that's the case, both d pi and L nu in their rest frame. And so that means that somehow I'm putting together visualization corresponding to different rest frame, but that's useful to get an idea of how things are implemented. And so you measure, you have different angles that will help you to define in their respective rest frames the angle of the D, the angle of the lepton, and then the relative angle between the two planes corresponding to the two emission on the hadronic and the leptonic side. And so when you want to describe what's going on, when you have this kind of, so in the end, what you want to have is some kind of description that will be both description with respect to the variation of Q square, which is the invariant mass of the lepton pair. So you want to have this kind of expression for that will cover all the elements that are inside the description of your decay. And so for that, what you will say is that you have first to describe to compute the amplitude through the effective Hamiltonian, so that you have already taken care of the separation between masses and short distances and long distances, sorry. And then when you think of what you will have, so if you're focusing on the contribution from one specific operator, so that means that you will have a Wilson coefficient, a term that will be just given to you by the bilinear corresponding to the lepton part. Then the part that will give you the CKM matrix, not the CKM, sorry, the matrix element for the B to D star transition. And then you will have also something related to the propagation of the D star, and then something related to the decay of the D star into D pi. And actually your differential decay rate is going to be proportional to the sum of all these contributions. So you see that actually you're going to get interferences between the different amplitudes. So if you want to see to see how to express now, obviously you could do that in a brute force computation. I mean, if I'm giving you all the expressions of the various matrix elements in terms of the form factors, then you can just say, okay, I just compute everything. And then in the end, I will get a very complicated expression that will involve the various different form factors, the different Wilson coefficients multiplied by some polynomials in my angles, and that's it. That's true. That's also not necessarily the best way of organizing the discussion, because obviously you do have quite a lot of information concerning what are the various operators that can contribute to this. You have quite a lot of information about the spins involved and the conservation of angular momentum that is at play and so on. So it's certainly more clever to try to find a good way of expressing this kind of computation. So for instance, if I consider an axial or vector operator, so already in the standard model, so that means that actually my two matrices, Dirac matrices that are involved inside the operator and that I'm separating in two sides, they will carry a Lorentz index. And actually it proves interesting to think in terms, because you've got this Lorentz index, in terms of the polarization already of the intermediate state, the D star. And actually you can think also that there is a W, virtual W that is present here, and that will also be responsible for the, will carry some kind of polarization. And so that's why it's then interesting to think in terms of, or V, let's put it V, that's for me. So you've got this D star, which is present, which is on shell, almost on shell, narrow, and then you've got a virtual intermediate boson that will go into Nu, both of them having polarizations. And then you can say, okay, I will introduce complete set of polarization vectors. So typically, in general, if you do that, that would be vectors with the three actual polarization that are the real ones, so 0, plus, and minus, and then you've got a unphysical time-like polarization that you have to add in order to have a complete basis, and then you can use the completeness relation that you have here that allows you to re-express the tensor G mu nu in terms of this polarization. So it's omega star. Where G lambda prime is just 1 minus 1 minus 1 minus 1. But this time it's really in this polarization space. So where you can have T and 0 plus minus 0 here. So you do have a 1 only for the time-like polarization and physical polarization. And then actually you will consider separately, so you will use that, but for two different sets of polarizations. One which is, so if you call epsilon the one that will be related to the would-be virtual intermediate boson here, and then eta for the D star. Then actually the matrix elements that you have, you can re-express them involving those polarization vectors. So if I got this, I can just say that actually it's a combination of different terms corresponding to given polarizations. I will put epsilon star here, nu lambda, G lambda lambda, and nu and bar gamma I nu I n nu here. And so that's for the moment I've just written a tautology. I'm just saying that this summation over lambda will just give me back G mu nu, and but I've dotted it so that I've separated, I've created a term that is depending on the polarization. And the same thing goes for Hi mu. I can do the same. H. Yes, I'm missing a nu here, and there is a nu here missing. Here we are. And this I call Hi lambda. Okay, so that's quite trivial, but then the point is that when I'm doing the computation of my the sum of all the contributions that I have to take to model square in order to compute the decay rate, then what I end up with is something quite simple. So I'm forgetting for the moment the question of the propagation of the D star, but that's something that can be taken care of afterwards. And so the thing is that you see that in this way, if you're choosing the polarizations so first of all, you can choose the polarization in different rest frames, and actually that's what you're going to say. You're going to say, okay, epsilon is really related to the polarization of the lepton part, eta is related to the polarization in the hadronic rest frame. And then that means that actually you have quite a large simplification of the possibilities of amplitudes here, or combination of polarizations that can actually be of interest. So in the respective rest frames for leptonic and hadronic, then that means that actually you will find that the only possibilities that you have for this combination here to be different from 0 is actually when you've got either, so that's for the leptonic and this for the hadronic. So if it's time-like for the leptonic part and 0 for the hadronic part, plus 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 minus minus, or 0 0. So here T is still allowed for the virtual intermediate state, this virtual intermediate gauge boson, this W, whereas here D star is considered as being real, and so there is only 0 plus and minus polarizations that are allowed. So that means that actually the decay is going to be, you can analyze the decay as interferences of amplitudes with definite polarizations of the D star and the V. So that helps you a lot to analyze everything in terms of simple polarization. And the point is also that that means that each involves only very specific combinations of form factors, because there are, those combinations are associated with a definite polarization of your D star for the hadronic part. And also that means that actually you can afterwards analyze much more easily the contribution of the Wilson coefficients. Because actually not all operators will be able to send you to a particular polarization state. So it means that you can separate in a nice way the various contributions. So I'm not going to hammer the whole structure. That wouldn't be very very useful, very informative. So just to tell you that in the end, you will be able to express this decay rate in terms of some angular coefficients that you can measure. And then actually in the end, you can build 12 observables this way. Which are which are interferences of helicity amplitudes of the form I've just mentioned before, which contain this kind of contributions from the effective emission. Okay, and so once you've got this, so you can, for instance, if you remember, apply this in order to compute, let's say, the longitudinal polarization of the D star or the polarization of the tau in terms of the Wilson coefficients. So now, what can we do to do the interpretation? So we can just, so we can try to extract the new physics contributions in the CIs. So in principle, yes. So in principle, what you would do, and that's what you're going to do afterwards, is to say, okay, I've got a large number of, or I've got a set of data depending on Wilson coefficients from the theoretical point of view, then I can do so some kind of fit to the data to extract the CIs. That's something that would be the natural thing to do. However, for the moment, not so many data actually, because as I said, you've got this RD star, you've got this polarization of the D star, you've got this polarization of the tau, and not much more for the moment. So the idea is not so much to do that for the moment, but rather to say, okay, here I observed a deviation compared to the standard model, and it's more or less the same deviation in both cases. And then here in the, so that's for the branching ratios. And for the angular observables, not much for the moment. So it seems standard model like. So actually, one way, very easy way to start doing this is just to say, okay, if I want to be able to reproduce that, there is a very simple solution. It's just that you have just to change the value of CVL for the tau. So I remind you that this is the Wilson coefficient for the standard model. So in other words, to say that the Fermi constant for the tau B2C tau nu is different from GF for B2CL nu. And that would be enough to generate exactly the same shift in RD and RD star. And since you're not modifying anything, so it's just the absolute branching ratio that you're modifying, you're not modifying anything concerning the geometry, respective geometry of B2D star tau nu and B2D star nu and so on. So that would be a very simple solution for that. So obviously, you may want to check whether other operators could do the job, but not necessarily in the same way. I mean, maybe they could just modify slightly the angular observables, but you don't have so many of them. So you can imagine that you would have the possibility to change a bit within uncertainties those angular observables, and also change by 10% what is expected, the ratio, the value of RD and RD star compared to the standard model. Actually, what happens is that it's not very successful because the tensor contributions tend not to go in the right direction when you want to explain the longitudinal polarization of the D star. And in principle, you could play with right-handed vector and pseudoscalar couplings. But actually, when you need to have quite a significant change, it's of the order of 10% once again. And so that means that you will face actually the bounds that come from something which is not actually measured, which might sound a bit contradictory. It's a BC to tau nu. Why is that? It's because it has not been measured, but it cannot be more, cannot exceed the total width of the BC, which has been measured. In other words, the branching ratio cannot exceed 100%. And so the thing is that operators, especially pseudoscalar and scalar operators, entering that would be present at the level of the effective Hamiltonian have a large contribution, an enhanced contribution concerning BC to tau nu. And so if you want to explain RD and RD star by this kind of pseudoscalar or scalar couplings, it becomes very difficult because you start being in the region where you start having very large contributions to BC tau nu. We are borderline in the sense that it's not really 100%, but it starts being very large. Further constraints that are also not really going in favor of tensor or right-handed vector or pseudoscalar couplings come actually from LHC, but really LHC in the Atlas CMS way of thinking. How is it? It's because you can imagine if you have this BC tau nu contribution coming from any kind of operator from new physics, then you may imagine of, even though it's very rare, you can imagine to pick up a C, a B, and a C charm quark inside the proton, and then being able to interact through this, the same operator, and the underlying physics corresponding to new physics being involved here. And in that case, you would find in the end coming out of your collision a very energetic tau and associated with nothing, because you got the neutrino that is flying away. So you're looking at something that would be tau nu x. And there are measurements of these objects. And so if you have something which is an operator, a contact term, you would expect that it will change the distributions of your events, of the tau. There would be some kind of tail of the tau that would be modified in this way. And then after, even if you start increasing in energy at some point, resolving the contact term, and you don't see anything of this kind. And this, once again, is affecting quite significantly the various operators that I've just discussed before. So in the end, at the current moment, it seems that this the explanation that is the easiest one is actually the best one on the market, being this affecting essentially just the standard model operator already presented at the level of standard model, but changing the value for the case of the tau lepton. Then one thing which you can imagine still doing, and afterwards I'll do a short break, is to look at single mediator explanations. So for the moment, I've remained just at the level of the effective theory, so the low energy level. You can say, okay, I'm trying to build a full explanation through a complete, ultraviolet complete new physics model for this particular change. Clearly, you can do it in many different ways, but actually what people tend to think is more something along the lines that I can try to explain the shifts of the EFT with the presence of a single new degree of freedom of intermediate mass, meaning something that would have a mass which is between the typical scale of all the new physics, all the new particles. So the first hint, the tip of the iceberg, if you want, of the new physics model that happened to be a bit lower in masses. And so that's why we're bumping into this first element, this first realization of the new physics degrees of freedom. And so it turns out that if you think in terms of what they could be, so the problem is that if you think in terms of, so you need something charged, so that could be a charge Higgs, but then it would have scalar couplings, and I just mentioned that scalar objects or scalar operators are not very much in favor because of these constraints from BC to tau nu. Then you could imagine excited gauge bosons, W prime, and actually that would be your most natural IG when you start thinking of how to change the standard model operator. But actually the problem is that here you would have also Z prime involved, because you would think immediately in terms of triplets. And those ones, they would actually affect neutral meson mixing, especially BG, BS, especially BS mixing. And so that actually, when you try to play with the effect that you need in order to generate the shift for B2C tau nu, you end up necessitating a very large contribution to neutral meson mixing. One thing that I did not highlight, and that's a good moment to do that, is be careful that we need a shift of 10%, of order 10%, compared to a standard model tree-level process. So that's something which is not so negligible. And if you start saying that you need a coupling of your new degree of freedom, which is quite large, or a mass which is quite low, and so this is fine, and you can imagine doing it. But then when you start saying, oh, but I've got a W prime with this large coupling or this low mass, that means that the Z prime associated with that will also have such a large coupling or low mass. But then you start saying that this Z prime will be involved in processes that in the standard model are loops. So that means that you will have a Z prime contributing at the typical level of a tree-level standard model process with respect to what is a loop-level process in the standard model, being the neutral meson mixing. So that's the reason why, even though it might seem a reasonable shift at the level of the B2C LNU transition, that will be an enormous shift in neutral meson mixing, because you start having something of the scale of a tree-level contribution competing with what is a loop-level contribution in the standard model. So that means that those explanations are not very satisfactory, but there is one which is also possible is leptoquarks. So for the moment here, we try to have explanation that would keep the quarks on one side and the leptons on the other side. But actually, you could imagine opening the box. So here, what I had up to now was so I should probably remove that here for the moment. So here for the moment, I was trying to do something like this with my charges of W. But then the point is that I could also imagine doing something like this. And this would be leptoquarks. So clearly objects coupling both to a quark and a lepton. So that's something that is not standard model at all. And actually, when you do the, you look at, so objects that can decay into one quark and one lepton. So then you can look at all the possible combinations, taking various objects, quarks and leptons in the standard model. You end up with 6 spin 0 and 6 spin 1 possibilities, depending on the objects you combine from the quark and lepton point of view. And actually, from these 12 possibilities, 2 are good explanations for B to C time U. So one is a scalar leptoquark. So if I use the same notation I had at the beginning, that would be so obviously they're sensitive to the strong interaction. And the mass that you need in order to do that with couplings that are not completely impossible or ruled out, the mass of this object is of a few TeV. One thing that I want still to highlight is that this is a single mediator, so explanations. So you have to embed them in a UV complete theory. And actually, that's even more mandatory for U1, because actually, if you just had U1, this U1 leptoquark and nothing else, you would have divergences from the loops. So clearly, you need to have some higher, more massive degrees of freedom in order to do the to cancel out these divergences and get finite results. But so the general idea is that those elements, you put some kind of cutoff in order to extract or determine the contributions that you would have from loops in order to check that everything is okay. But for if you're just considering the tree-level exchange of this vector leptoquark, it's completely fine, and it explains indeed well B2C time. Okay, so I will stop for a few minutes, and I propose that we have the break now, and we'll convene in 10 minutes if that's fine for you.
Yeah, fine. Okay.
Okay, talk to you.
Okay, bye-bye. In the 49, I will write down. So
after having discussed a bit B2CNU, I'm going to talk briefly about the second place where there seems to be deviations for the moment, which is B2SLL. So that's the place where you got more deviations actually than can be identified. So I already mentioned that there were 2 ratios comparing problem lepton flavor universality that were deviating from the expectations. So actually, and I didn't mention that before. So when we look at when we looked before at RD and RD star, actually the value from the standard model of RD and RD star is not 1. It's far from 1, because actually the mass of the tau is very different from the mass of the electron and the muon, and so obviously you do have quite large kinematic effects related to that. So even though you have an accurate prediction for this because you know where the form factors, you do have quite a lot of differences between the weights that you put for your different form factors contributing in the standard model. You remember that you had several of them, even for B2D, you got F0 and F+, and the weights that you have are dependent on the masses of the electrons. And so because the mass of the charge is different from the mass of the electron, the muon, that means that the prediction for the branching ratio, even in the standard model, are very different. The ratio is well known, and so that gives you a value which is accurately predicted, but which is different from one in the standard model. When you're looking at B2SLL between electrons and muons, the fact that you've got very small masses for the electron and the muon compared to the other scales involved means that actually when you're measuring these ratios, you expect values that will be close to 1. And so for RD and RD star, you measure over the whole spectrum. For B2SLL, so for RK and RK star, actually, you don't measure the whole spectrum. I'll come back to that later. There are good reasons for you to remain in a window which for the value of the invariant mass for the dielectron pair, which is called Q squared. So for mu or EE, which is not very large, you prefer to keep it low. And so you're measuring in this for the branching ratio for these low values of Q squared. So that corresponds to a large recoil of your K or your K star meson during the decay of the rest frame. And so you see that actually there have been measurements from LHCb over time that have progressively confirmed the fact that you're far from, not very far, but the uncertainty matters as much as the central value here for RK, and as well for RK star. You see, so all these funny dots with colors correspond to the theoretical predictions, which are very close to 1, not exactly 1 when you're at very low Q square, but there's a good reason for that, that you understand. And the measurements from the LHCb collaboration have shown that the values observed are quite small compared to this. There have been complementary measurements in isospin related modes that confirm with a lower accuracy the same trend of having a deviation from the expectations from lectern flavor universality. And at the beginning, as I mentioned, those two kinds of decays, B2C and B2S, I said that if in the B2C case, the main culprit of something going on is RD star, for B2SLL, there are more places where there are deviations. So first, the fact that you've got these deviations are actually essentially due to the fact that, or can be seen already at the level of deviations for B2K mu alone and B2K star mu alone. Actually, there are deviations, even BS to phi, lambda B to lambda mu, and BS to mu. So several different processes with all the same B2S mu underlying physics have branching ratios that are not in good agreement with the standard model. Obviously, the uncertainties are larger because you have hadronic uncertainties that are cancelled out in RK and RK star that are not cancelled out when you're looking at the individual branching ratio. For B2S mu given B2S mu transition, but they all go in the same with the same idea of a suppression. And then the second thing that I mentioned is that you can measure also the angular structure. So exactly like for B2D star tau nu, we had some information about some geometrical aspect of the decay. The same goes for B2K star mu. So clearly that's more interesting from the geometrical point of view to have a spin 1 object at the end. So that's why you like to have B2K star mu. And then I show you here a few of the angular observables that are available. I'm actually going to detail that a bit more, but you see that you have the longitudinal polarization that is present. You have the forward-backward asymmetry that corresponds to asymmetries in the direction where one of your muons, so you've got a muon and anti-muon, let's say the muon is is emitted in the same direction or the opposite direction compared to the K-star 0 direction. You have obviously to put a few rest frames in my statement for it to make it sense, but that's the general idea. And then you have on the bottom half what is shown for a particular angular observable, so one of the many angular observables that you can have. And actually the difference between the two plots, S5 and P prime 5, is actually the way you define these angular observables. I'll come back to that in a few moments. So that in the end, for P5 prime, you have, you can see in a heightened way the discrepancy between theory and experiment. And you see that as you increase slowly Q squared, so I remind you Q squared is the dielectron invariant mass. So that corresponds to when you increase Q squared to have a lower recoil, if you want, and for the K star. And you see that when you increase Q squared, then you start having a departure progressively, whereas for the other observables, so you might see a bit of something for AFB, maybe the forward backward asymmetry, a bit of something for FL, but it's very weak. Whereas for P5 prime, you start having deviations at the level of 3 sigma between theory and experiment for the two bins that you see where there is a discrepancy. So you do have, as I said, okay, so obviously this is only a small except of all the possible observables that have been measured concerning those various modes. But that's telling you that actually there is more to dig in terms of deviations or absence of deviations of the standard model. And I, once again, I emphasize that here the fact that you have deviations only for some of the observables, but not for others, is actually giving you directions to look for new physics. Exactly like before in the case of B2D, B2D star, I said I have something concerning the branching ratio, but nothing about the geometry. So certainly that means, well, certainly, at least a good explanation is something where I'm just changing the value of the standard model with some coefficients and nothing more. Here you see that the situation might be potentially more complicated because you've got also elements of deviations coming when you're considering angular observables and not only branching ratios. Okay, and so now I come back to a more illustrative way of describing what's going on. So still with the same idea. And here, because of the more complicated nature of the problem, it's really important that we try we stick to the same approach, and that's going to be what we do, to try to analyze the impact of new physics, of the various sources of new physics on the observables that we measure, because it's a highly non-trivial thing to determine which observable, angular observable, for instance, is going to be affected by which operator, which new physics contribution. So I already mentioned that a bit when we were discussing B2S gamma, but the effective Hamiltonian for B2S LN, so same story as before, and that's also why I spent quite a bit of time on B2C tau nu, because you could have said, oh, well, it's quite easy to make that even without this formalism. For B2SLS, that's probably not the same. So once again, when you're considering the various contributions that can come already at the level of the standard model, you see that, as I already advertised before, you've got more possibilities, in particular, depending on whether you're considering a charm, an up or a down quark. In your loop, in some cases, you shrink everything to a point, and that's going to give you O9 and O10. So two contributions that will have the structure reminiscent of the B bar, L bar. And you've got those two contributions because you've got the Z that can give you particular both of them, whereas the photon would couple only to the vector part. Here for 9, and then you've got O7, which is giving you, so I should say proportional because you've got different normalizations for this one. Well, it's bar sigma mu nu. Sorry. B, well, B, I can put it here. And the fact that I've got F mu nu, it's because I want to have something which is gauge invariant. Couldn't have just A mu coming in, so that means that there is a derivative. So that's going to go with a power of Q, Q mu or Q nu when I'm doing the computation. So the fact that 1 minus gamma 5 or 1 plus gamma 5 is obviously related to the structure of the weak interaction. And also the fact that you can use the idea of matching and running in order to get your value of this operator, the Wilson coefficients of this operator at a high accuracy. And the fact that C9 and C10 are close to be opposite is also a reminiscence at some level of the V minus A structure of the standard model, even though it's not only that, there is also quite a bit of numerical aspects of the hierarchy of masses involved that is responsible for that. So that's in the standard model. And then exactly like before when we were discussing B2C, you can imagine doing having not only deviations to the standard model coefficients, but also to have additional operators. So let me just add that, so these are the, how to say, the not necessarily, well, yes, main operators for the discussion, but actually, as we will see, this is not exactly the end of the story. So new physics in deviation of C7, C9, and C10, or you can have additional operators. So once again, you can have chirality flipped operators. So that corresponds to just taking 1 minus gamma 5 or 1 plus gamma 5 and replace it by the opposite chirality projector. And so that means that you've got in the quark bilinear. So these ones are with prime. Actually, they're already present in the standard model, but very much suppressed. Actually, there is suppression MS over MB, so that's why you don't see them. You don't get them as being the main operators. But in the presence of new physics, obviously, they could, in principle, reach the same level of deviation of the same values as the standard model one. And then once again, you've got scalar, pseudo-scalar operators. So for instance, thing, so it's prime, P prime. So for instance, something that would be and also tensor operators. Okay, and as I said already before, the thing is that you should be careful with this kind of more complicated transitions, because you do have also other contributions which are not local, non-local contributions, where actually you've got the charm loop that you do not integrate, you let propagate, and then here you've got a contribution from the W exchange, so 4-quark operator corresponding to a W exchange. So you just shrink this part of the diagram to C, and this is something which is completely authorized from the point of view of the effective Hamiltonian. You're drawing a diagram with all the degrees of freedom that have still the ability to propagate. And so the thing is that because you have this charm loop, and then here I wrote only the version of the diagram in the simplest version of the diagram, but you can imagine that you've got exchanges of gluons between all those quark lines. And there will be also the problem or the issue that in some values of Q square, this particular CC bar pair will become resonant. And so that's the reason why in the B to SLL transitions, you don't have this integration over the whole space. You do have to take care of the possibility that in some ranges of Q square, you will have large hadronic contributions that are essentially driven by resonance dynamics, which has nothing to do with new physics, it's just purely standard model. So that means that when you think of drawing what's happening when you have a value of Q square, which is once again the dilepton invariant mass, you start at 4 mu square. Then you end up at the endpoint here. As I said before, you have you have a region which here corresponds to a low recoil of your K star, if I'm looking at B to K star. Here you correspond to a region with a large K star recoil. When you're going at Q square very small, then you start being very much sensitive to the case where you do have the lepton coupling to an almost real photon. So that means that you will expect that at very low Q square, you have something that corresponds to the photon pole, or the proximity of the photon pole, let's say. But then, so you have to start something like this, and then at some point when you reach the mass of the J psi, which is the first CC bar, resonance, then you will have something that will be like a bright Wigner peak. Then you do have a second resonance for the psi 2s, so excited state. And then you will have wiggles that will correspond to more and more excited states, broader and broader CC bar. And so actually they will average around a value which will correspond through the quark hadron duality to something that will be close to the perturbative value, but close means still that there is some uncertainty attached to this fact that it's not exactly the perturbative answer, but if you integrate over a broad bin, a broad range, probably they will average out to yield something close to the perturbative expectation for this CC bar contribution. And so you see that once you have this, then you can imagine to do things of interest in two regions. One which will correspond to this large K star recoil, and one which corresponds to a low K star recoil. So these are typically the regions that I already discussed, which are related to two different tools in order to tackle the form factors. So light constant rules on one side, lattice QCD on the other side. Then I mentioned already that you have an effective theory when you have something which is just related to just soft physics coming out of the decay of a heavy quark. But actually, you do have also an effective theory which comes into the game in the exact opposite direction. So here it's heavy quark effective theory. Here is soft collinear effective theory. And so, just to remind you, those two effective two effective theories of interest, I should rather say, because otherwise because my point is that you can have, HQET, which is the situation where the K star energy is small compared to the mass of the B. So you express everything in terms of soft physics. And as we discussed last time, you have a situation, so soft gluons and quarks plus heavy quarks, but those heavy quarks actually, they are more or less like there are also soft degrees of freedom, because once you take out the trivial component that comes from the B meson momentum, actually there is only residual momentum, which is also soft. So everything is soft actually in this heavy quark effective theory. And then you've got the SCT case, where the energy of the K star is of the order of MB. And then that means that you have to take into account not only soft degrees of freedom, but also collinear degrees of freedom. So what does it mean? It just means that actually you have light-like directions that correspond essentially to the direction in which the K star is flying. And then along that direction, you can see that a good approximation in this situation, in the limit where you're flying along a light-like direction with a very high energy, is that your K star is actually made of collinear partons, so quarks and gluons, and that you can describe as a first approach just the physics involved as being soft and collinear degrees of freedom, and then the collinear patterns will feed a K star that is going to be the description will be a good first start with 1/MB corrections afterwards to that. And so that's possible to do that, and in both cases, then the fact is that because you integrate out the other degrees of freedom, so they will correspond to perturbative corrections. For instance, that's true for the hard gluons that will go into short distance coefficients of your effective theory, and then you remain with an effective Lagrangian corresponding to each of these two theories with some decoupling between the QCD degrees of freedom. Typically, that's what we saw concerning the HQET case, because as we saw, the fact is that the spin degree of freedom of the heavy quark is not playing a role anymore once you've did this integration, you've integrated out all the hard gluons, and what remains are only soft gluons that don't care about the spin of the heavy quark, the heavy source of color of the B meson. So that's the same thing that occurs for SCT. Since the theory is more complicated, because you see that you've got many more degrees of freedom that are present. I'm not going to spend time writing down the equations, also because the apparatus is quite complicated. But one thing is that you have from this, so in particular, in both limits, so K star energy being very small or very large, you have a simplification, you have fewer degrees of freedom, which means that there are relations between the form factors. Those form factors are different because they're probing different configurations of your B and your K star and the interaction. But if you're telling me now that some of them are irrelevant in these limits, that means that the form factors that I thought to be different are actually identical in those limits. And so that's what's happening. So if you think in terms of the form factors that are needed for B to K, I'm already considering all the form factors needed, including those only needed for the new physics description, not only the ones that are needed for standard model 1, B to K star. So actually you've got 3 for B to K, 7 for B to K star. And then if you take HQET, so lower record of the K star, actually you remain with only 2 and 3, respectively. If you try to do SCET, then it's 1 and 2, so that's a simplification. And then what you end up with is actually that a typical form factor is going to be something defined as a soft form factor of the effective theory, plus order alpha S corrections coming from the exchanges of hard gluons and so on, plus 1 over MB corrections, because this comes from considering the situation in the MB to infinity limit. So F, these are the full form factors. So those are the 3 or the 7 form factors I was discussing before. Then you can say that actually they're related to a subset of soft form factors, fewer of them. So that means that when I'm looking at several different form factors, for instance, for B to K, that's going to end up, for instance, F0 and F plus are going to be given by the same reduced form factor in the SCET limit. And then this SCET limit has corrections of 2 kinds. Some of them are just due to the short distance physics, and so that's computable perturbatively. Alpha S corrections that I can compute, but then there are also 1 over MB corrections that are harder to compute. So this is for the, so that's one way of reducing the impact of hadronic uncertainties. So that's coming from the form factors. But actually, the point is that, as I discussed before, you have 2 different sources uncertainties. Because if you look at the transition that I wrote before, so in the end, whatever nonsense occurs at the level of the effective Lagrangian, Hamiltonian, sorry, what happens is that you can separate the contributions in terms of their couplings to the leptons. And then what you have are couplings which are vector axial. You've got local contributions. So one which is A mu that is going to be actually involving C7 and C9 here, whereas B mu is going to involve C10 times form factors. But you do have also a contribution here, which is non-local, coming from CC bar contributions. And the point is that this will affect only the vector contribution, because when you look at the CC bar, the only remaining way of producing a lepton, since you've integrated out already everything that had to be integrated out, is through a photon. So that explains why you do find this contribution only through a vector coupling to the leptons, but not otherwise. So it will contribute together with C7 and C9. However, there are some differences, because C7 and C9 are just short distance universal coefficients. If you're looking at any kind of B to S LL transition, whether it's B to K LL, B to K star LL, and so on, that will still be the same coefficients involved all the time. Whereas here, this term, CC bar contribution, you see that actually most of its danger or interest, that depends what you want to say, comes from the fact that it can interact. There are gluons that can be exchanged here, meaning that this kind of contribution is going to be Q-square dependent. It's going to be final state or external state, final state, hadronic, initial and final state dependent also, because it's really related to hadronic physics, so long distance physics. So it doesn't mean that you don't have to compute it. It doesn't mean that you can neglect it. It just means that it has different properties compared to what you had before concerning the short distance coefficients C7 and C9. And actually, I'm not going to dwell on that, but you have different estimates or computations of these contributions that are present. Okay, so I think that since I'm running a bit late, I will just say one word concerning the fact, how do you tame these hadronic uncertainties? So essentially what has been done is to focus on reducing the uncertainties coming from the form factors. And that's already something that is done by considering the ratio RK and RK star, because, as I said before, you do have the same for the prediction in the standard model or beyond, you would have the same hadronic form factors involved upstairs and downstairs. So that means that by doing this kind of ratio, you're expressing everything in terms of ratios of form factors that are generally better known than individual form factors, and you're reducing the uncertainties attached to that. So that means that actually you do have, that's one of the reasons, it's not the only one, that's one of the reasons why you do have so much ability to derive precise predictions, especially in the standard model. Once you start having new physics coming into the game, the cancellation of form factors is not as efficient. So that means that there is a slight increase of the uncertainties in the presence of new physics. And that's it remains rather clean observables in the sense that they're not too much polluted or too much affected by hadronic uncertainties, but still they do have some elements of uncertainties from the form factors. They also have elements of uncertainties inside due to the CC bar contributions, which are also present upstairs and downstairs. They are the same. Because those contributions are dependent on the hadronic incoming and outgoing state, but not on the flavor of the leptons. However, they are the same. That doesn't mean that they cancel, because they're only one of the many contributions that are present inside both the numerator and the denominator. The thing is that I will not spend time on this, but the same thing has been done for angular observables. So you can measure, you can derive once again this awful angular distribution of B to K star, for instance. Then you can define this way many angular observable. I've got a dozen of angular observables that are present, that are just interferences of LCT amplitudes again. And the point is just that we can use HQET SCT to identify combinations of angular observable depending on a single reduced form factor. You've got plenty of form factors involved in each of these angular observables, because the amplitude, LCT amplitude combined, many of them. But then in the limit of HQET or SCT, they collapse to very simple identical soft form factors. And then the idea, so obviously this is on the inner limit, and then you've got corrections to this limit, one over B corrections, other alpha is corrections. But the idea is that you can then take ratios of these angular observables so that the same reduced form factors gets cancelled out. And so among the many observables that you had, I showed you P5 prime, and I told you that it was some kind of improved observable compared to the initial angular observable, and it's improved in that sense. And so that means that it's less affected by uncertainties from form factors. You do have a limit where there are no uncertainties from the form factors. Obviously, you've got corrections to this limit, but that means that P5 prime is less affected, and you can build other angular observables similarly that are less affected by this kind of uncertainties. So I will just take very few moments in order to say that you can do a fit to constrain new physics in the CIs. And so here, contrarily to B2 theta nu, you've got a large set of observables. Actually, the current fits are doing something like 250 of them, and that's only if you take CP average. So you're not assuming that your new physics is CP violating, which is a possibility that's probably to explore in the future. And then you fit the various coefficients, and I'm just going to show very quickly two possible outcomes, favored scenarios for this. And so that's going to be here. So among the scenarios that are very much liked, all of them like to have a large contribution to C9 in B2S mu mu. That's something which is clear. But you have also new physics, so shifts in the Wilson coefficients for both C9 and C10. So that's the Wilson coefficients that you do have in the standard model. So shrinking everything to a point, but with different couplings to the leptons, vector and axial. And you see that you're compatible both with a situation where you've got only C9, but you can also have the situation where C9 equal minus C10 is also possible and interesting. You've got also on the right-hand side another scenario, which is C9 and C9 prime. So this time C9 and the Cayley flipped operator for the S bilinear. And once again, you see that you're compatible with C9 only, but also C9 equal minus C9 prime. The point is that, so you could play with plenty of different scenarios, assuming that new physics enters only one or two Wilson coefficients. I'm just showing those ones because they are the more efficient to explain most of the deviations without hitting problems with places where we don't see any kind of deviations. And actually, because you're solving many discrepancies, when you add up all the discrepancies, the difference in the power of explanation between the standard model and those scenarios is quite large. You add up deviations by 1, 2, 3 sigmas, and in the end, you're solving a combined deviations up to 7 sigmas between the standard model and those scenarios. So that's quite interesting. Especially C9 equal minus C10, you can imagine that it's really keeping the V minus A structure of the standard model. And so this one is just by keeping the situation where you have, you assume that you got only B2S mu mu affected by new physics and nothing more. I should also say that you can say that because of the number of hadronic uncertainties I discussed before, you prefer to keep only data where you have indication of cancellations that are important. And so typically quantities probing lepton flavor universally violating quantities like RK, RK star, or quantities where you have only a very limited input of hadronic uncertainties like BS to mu mu, which is electronic decay. So you've got only the FBS decay constant being involved and not many form factors. And you see that even though it's less powerful, you go into the same direction. You do have a similar information. Obviously, that's a subset of what I showed just before. So, but at least it's a compatible and going into the same direction on pushing you away from C9 standard model. And then the other thing that I can discuss quickly is the fact that you have, even though you have mostly deviations in B2S mu mu, I said that B2S EE is not necessarily very clear. You can still think that there might be some lepton flavor universal component in this new physics. And actually, you can see that by putting together information from the various experiments, actually, you do have a situation. So these are two scenarios that are, that are among the ones that can be interesting for new physics with a universal and a non-universal component. Actually, I realize now that I don't show the ones that are the most interesting, but that's not really a problem. In general, at least you do have contributions. You can explain better the data by adding a small piece that is universal, that is affecting both B2S mu mu and B2S EE, but not so much. So just as a final comment, just to say that you do have, just to make the equivalent of the discussion that I had before, and just very briefly. So you can ask yourself again, since you do have these contributions to the Wilson coefficient, so do you have single mediator explanations for this? And so actually you do have, if you're just restricted to B2S LL, two possibilities, Z prime with appropriate couplings, but also explanation with one or two leptoquarks. And so in particular, one situation which was, I'd already indicated, but which is quite favored very, very often, is easily explained by the same leptoquark that we showed already popping up in the case of B2C and nu. And so you can think of embedding this leptoquark in a larger new physics model in order to get a combined explanation. So that opens the possibility of a combined explanation for B2S, LL, and B2C time. And I will not dwell too much on that, but that's something that indeed is possible. Since we're looking at combined explanations, there are also other possibilities combining two scalar leptoquarks, and you have on the market several possibilities for this. I must say that exactly in line of what I said for B2C, there is no successful explanation with hexes or WZ prime contributions. Okay, so there would be certainly more to say, but I don't want to go too late. So just to finish, and now, so the point is that obviously that's still a field that is evolving with the experimental input that you receive. LHC is still gathering data. Actually, we did have still last year a few more hints, not at the same level as RK star that I showed, but the companion isospin-related modes were measured with the same kind of tendency to violate electron flavor universality. So that's still something that will be very interesting to watch with the restart and the new sets of data gathered by HCB in particular, but not only. You do have also to expect things from CMS and Atlas. You've got the upgraded version of Bell, which has started in Japan. So that's very interesting because you will have new data coming from a completely different environment. Rather than a proton-proton environment, you will have an E+, E- environment. There are types of time-dependent analysis, for instance, that are you can reach with Bell2 or related to the tau reconstruction, identification of the tau, so modes that are not necessarily easily accessed at the LHC. So, and also just the fact that the systematics will be completely different. Clearly, on the theory side, the hadronic effects have been, will still be studied in great detail. There are plenty of things, not only concerning the pure improvement using well-known techniques like lattice or light consumables, but you have also additional questions concerning, for instance, the fact that we are talking about B2K star, B2D star, but actually they are not completely stable particles. So these are, they have a width, so what is the impact of that? And for the moment, as I said, I've not touched upon the question of CP validation in these modes. I've talked before about CP validation in the standard model. I've talked about these deviations that we see, but I've tried to explain them with new physics, short distance physics that is purely real. So there are no new phases. So this question will certainly be of interest now to try to see what's the room for new physics that has some CP validation for these decays. Okay, and so that thing that there is much more to come on all these sides, so that will keep being quite exciting. And so to wrap it up, I've tried to show you during this set of lectures that flavor is at the same time a very interesting tool to probe the standard model, but also to probe new physics. In both cases, that's related to the hierarchy of quantities, masses, couplings that are present already at the level of the standard model, the capacity of having a quantum sensitivity to higher energies. Clearly, it's also challenging because of these various scales involved, because in particular, you have to play around both with perturbative and non-perturbative physics. But it has clearly quite a large potential, already proven, but still to be developed, concerning the extension, the understanding of the standard model, and the determination of potential extensions, explaining its shortcomings. Okay, I thank you very much for your attention, and I hope that you enjoyed this as much as I did.
Okay, thank you very much, Sébastien. That was really a nice final talk of a nice series of lectures. And unfortunately, you will not be present, as you said, in the discussion section this afternoon. So I encourage some student that has some urgent question, but to pose it now, or you can always pose it to Sébastien through the Slack channel that we have. So
yes, absolutely, I am.
Oh, there is a team that wants to ask something.
Sure.
Yeah, just a quick question on this one vector quark. Are there any constraints, because you said you have to embed it in a larger gauge group? How is the prospects there? How is the progress?
Okay, so the thing is that you do have constraints internally, if you wish, because you want to be able to explain both sets of deviations, so B2S and B2C, so that actually when you play around with the constraints that you get from there, you see that if you want to keep the theory to be perturbative at the level of the couplings of your electron quark with the rest, and at the same time not having very large contributions to BS mixing in particular, because that's one of the main place where this can have an effect. Then you need to remain in a range of a few TeV for the mass of your electron quark, and then you tune the coupling so that you get the right amount for the processes that you're trying to explain here, B2C and B2S, without having too many problems with lighter generations, especially. So that's one thing. Then when you go for trying to explain that in terms of larger groups, then generally what you do is that you push the other degrees of freedom sufficiently high so that you still have this hierarchy between electroweak, this single mediator, and the rest, because otherwise obviously that falls apart. So you do have, if I remember, you do have a few possibilities concerning ground unified groups or Paty-Salam models where these could be obtained quite naturally. Well, naturally, it was not very difficult to obtain it, let's put it that way. So these are examples where this could be obtained in practice, and that worked.
Okay, thanks.
Okay, so Sébastien takes this virtual applause from everybody.
Okay, so thank you very much. I'll have a look at the Slack if needed to answer other questions.
Okay.